My name is Alexia Udol, and today I'm going to present to you Lab 4 Circuits from Physics 2212. The purpose of this lab was to predict the behaviors of circuits having resistors, capacitors, and bulbs in series or in parallel, using a voltmeter to measure the potential difference at different sections of the circuit, and finally, examine the behavior of ohmic resistors and capacitors. The physics principles present in this lab are energy and current conservation, including the node and loop rule, conservation plus definition of steady state, Ohm's law, and capacitance. For the preview of the results, the predicted calculations are accurate with the experimental results. For part 1 of the lab, 2 batteries, 2 resistors, and 2 ammeters were used to create a circuit. Predictions regarding currents 1 and 2 had to be made. Using the node rule, which states that current going in equals current going out, I was able to calculate the desired currents to be 0.02 amps. As you can see, the voltages of the batteries were added to be 3 volts and the resistors were also added to have 147 ohms. If the connection were to be reversed, the only thing that would change would be the sign of the current. The value of 0.02 amps would remain the same. Furthermore, when replacing one of the ammeters with a voltmeter, the circuit was open. This means that there is no current flowing through the circuit. So it marked that the ammeter had 0 amps. Next, the potential differences across different segments of the circuit had to be calculated using a voltmeter. The 2 batteries and the 2 resistors remained, but only 1 ammeter was used in the circuit. The current stayed the same throughout the circuit, but the potential difference readings did change according to which segment was being measured. Here in this image of the calculations, you can see the potential differences that were calculated. According to the loop rule, the change in potential difference round trip should be 0. When adding up the ones that were found, the potential difference did add up to be 0. Lastly, here you can see the data plotted in a graph which goes in accordance with the potential difference starting out as 0 and the potential difference ending and also being 0. Next, an ammeter was connected in parallel with a resistor. The current of the circuit increased to 0.06 amps. This is due to the fact that the current is not going completely through the resistor, thanks to the ammeter in parallel. More current is able to pass without it being affected by the resistor. Ohm's law states that voltage equals resistance times current. Since the resistance decreased due to the ammeter in parallel, the current of the entire circuit is bound to increase. The resistance had to be calculated as well for the 2 resistors, wire and ammeter. In this lab, we are making the assumption that the wires and ammeter have no resistance. When doing the calculations, the resistance of the resistors seemed to be a little higher than the value that they are supposed to be, which could be an error due to the precision of the measurements obtained of the ammeter. For part 2 of this lab, we had a 10 ohm bulb, and when connected to a capacitor and a battery in series, the bulb lit up, dimmed, until there was no light, which meant that the capacitor was charging. When connected to the capacitor, the bulb lights up, dims until there is no light, which meant that the capacitor was discharging. The charging time and discharging time of the 10 ohm bulb can be seen here, and the same thing happened for the 20 ohm bulb for the 2 scenarios, but it took more time for the capacitor to charge and more time for the capacitor to discharge. We are given the equation that indicates that voltage decreases exponentially. We had to find out the time constant, which in this case was RC, the negative reciprocal of the slope obtained with the data points. A circuit was set up containing a battery, capacitor, and a LiPo. Using this circuit, the voltage across the capacitor was measured as it was discharging. Here you can see that indeed the voltage across the capacitor did decrease exponentially, and was able to calculate the RC to be 6.90 seconds. The expected RC was 6 seconds, but there could be a source of error when recording the time and voltage manually in the simulator. For the what if questions, what if you were doing this lab in real life and used an actual ammeter instead of an ideal simulated ammeter? Here, in this case, the ammeter would most likely have resistance, so this would change the readings that are obtained for current. Finally, what if you were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? The capacitor would reach its full charge almost immediately, but this prediction would not happen in real life since other components of the circuit have resistance. So it would take time for the capacitor to charge instead of it being instantaneous. Thank you.